Navigating complexity. Mastering graph algorithms for optimal pathfinding graph algorithms form the backbone of modern computing, enabling solutions to intricate problems ranging from network optimization to artificial intelligence. These algorithms manipulate data structures composed of nodes and edges to model relationships and solve challenges efficiently. Their significance lies in their ability to process vast datasets and find optimal routes, detect patterns, and predict outcomes. Whether navigating roads, analyzing social media, or optimizing supply chains, graph algorithms provide foundational tools for developers and researchers alike. Fundamental concepts in graph theory. A graph consists of two primary components: vertices, or nodes, representing entities, and edges connecting pairs of vertices to denote relationships. This structure allows modeling complex systems like transportation networks or molecular bonds. Edges may carry weights, indicating costs, distances, or capacities, while graphs can be directed, with arrows specifying directionality, or undirected, symmetrical connections. Weighted graphs add layers of complexity, requiring specialized algorithms to analyze effectively. Graphs are categorized further based on connectivity. A connected graph ensures a path exists between any pair of nodes, whereas a disconnected graph contains isolated subgraphs. Understanding these distinctions is crucial for selecting appropriate algorithms. Degree. The number of edges incident to a node determines its degree, influencing centrality measures in network analysis. Cycles. Closed loops in a graph affect traversal strategies, necessitating checks to prevent infinite loops during exploration. Traversal techniques. Breadth-first search and depth-first search. Breadth-first search, BFS, explores a graph level by level, starting from a source node and visiting all neighbors before proceeding deeper. It excels at finding the shortest path in unweighted graphs due to its systematic expansion strategy. Depth-first search, DFS, conversely, dives deep into branches until hitting dead ends, backtracking systematically. While less efficient for shortest path problems, DFS is invaluable for tasks like cycle detection and topological sorting. Both algorithms rely on queues, for BFS, and stacks, for DFS, to manage node exploration. Their memory usage differs significantly, impacting performance on large-scale graphs. BFS example: finding the shortest route in a maze, where each corridor represents an edge. DFS example: solving puzzles like Sudoku by exploring potential solutions recursively. Dijkstra's algorithm: optimizing shortest path calculations. Dijkstra's algorithm identifies the shortest path in a weighted graph with non-negative edge weights. It operates greedily, always selecting the next node with the smallest tentative distance from the source. The algorithm maintains a priority queue to track unvisited nodes, updating distances dynamically as shorter paths emerge. Its efficiency hinges on the choice of data structure, typically a min-heap for O, V plus E, log V, time complexity. Implementing Dijkstra's algorithm involves initializing distance arrays, marking visited nodes, and iteratively relaxing edges. It guarantees optimality only when all edge weights are non-negative. Time complexity *** depends heavily on the graph representation and priority queue implementation. Limits *** fails if negative weight edges exist, necessitating alternative approaches like Bellman-Ford. Bellman-Ford algorithm. Tackling negative weights. Bellman-Ford addresses scenarios with negative weight edges, detecting negative cycles that render shortest paths undefined. Unlike Dijkstra's, it processes all edges repeatedly, relaxing them up to v-1 times. This iterative relaxation ensures even the longest possible paths are considered, making it robust against deceptive cost reductions. After completing iterations, a final pass confirms whether any updates occur, signaling a negative cycle. Bellman-Ford's simplicity comes at a cost. O(V*E), time complexity makes it slower than Dijkstra's for sparse graphs. Still, it remains essential for certain problem domains. Use case ***, detecting arbitrage opportunities in currency exchange rates. Drawback ***, inefficient for large graphs compared to Dijkstra's optimized variants. Floyd-Warshall algorithm. Computing all pairs' shortest paths. Floyd-Warshall computes all pairs' shortest paths simultaneously. Ideal for dense graphs with numerous queries. It employs dynamic programming, building upon intermediate results incrementally. The algorithm initializes a matrix with direct edge weights and iterates over all vertex combinations, updating paths by considering intermediate nodes. This three-layer loop structure gives it O(V) superscript 3 time complexity. Floyd-Warshall shines in situations requiring frequent all-pair computations, such as traffic congestion simulations. However, its cubic runtime limits scalability for massive networks. Advantage *** simultaneous computation of all paths simplifies post-processing. Limitation *** not suitable for sparse graphs due to high computational overhead. Advanced algorithms. And Johnson's method **search improves upon Dijkstra's by incorporating heuristics estimating remaining distances. This heuristic guides exploration toward the target, reducing unnecessary branching and enhancing speed in many practical applications. Johnson's algorithm combines Bellman-Ford and Dijkstra's strengths, reweighting edges to eliminate negative values. It achieves faster performance than Bellman-Ford alone, making it useful for graphs with mixed edge types. These advanced methods demonstrate how domain-specific optimizations can drastically enhance efficiency. Choosing the right tool depends on constraints like graph density, edge weights, and query frequency. Heuristic examples ** Manhattan distance in grid-based pathfinding, Euclidean distance in geographic mapping. Johnson's reweighting ** adds a constant value to all edges, preserving relative differences while eliminating negatives. Real-world applications of graph algorithms. Transportation networks leverage graph algorithms to optimize public transit schedules, reduce delivery times, and plan evacuation routes during emergencies. GPS navigation systems employ modified versions of Dijkstra's and ** for real-time rerouting. Social media platforms utilize graph theory to recommend friends, identify trending topics, and combat misinformation spread. Community detection algorithms reveal hidden clusters within massive user interaction graphs. In bioinformatics, protein interaction networks help scientists understand disease mechanisms. Phylogenetic trees constructed via graph algorithms trace evolutionary relationships across species. E-commerce ** product recommendation engines model user preferences as graphs to suggest complementary items. Finance ** fraud detection systems map transaction flows to flag suspicious anomalies in financial networks. Performance analysis and optimization strategies. Optimizing graph algorithms often begins with choosing the right data structure. Adjacency matrices suit dense graphs, while adjacency lists excel for sparsity. Memory allocation impacts both speed and feasibility for large inputs. Parallel processing can accelerate certain operations, though careful synchronization prevents race conditions. Implementing parallel versions of BFS or Dijkstra's requires dividing workloads intelligently across threads or processors. Approximate algorithms offer trade-offs between accuracy and runtime, particularly useful for NP-hard problems like the traveling salesman problem. Randomized methods balance precision with computational efficiency. Cache efficiency ** prioritizing spatial locality in memory access reduces latency for large-scale graphs. Heuristic refinement ** fine-tuning heuristics in a * can dramatically cut search space exploration. Common pitfalls and best practices. Misunderstanding graph properties leads to incorrect algorithm selection. Confusing directed with undirected graphs, for example, can result in flawed analyses or missed optimizations. Overlooking edge case scenarios, such as disconnected components or zero-weight loops, risks producing invalid outputs. Rigorous testing with diverse input configurations is imperative for reliability. Improperly managing recursion depths in DFS can cause stack overflow errors. Iterative implementations often provide safer alternatives for deep traversals. Debugging tip ****. Visualize small graph instances manually before coding to verify expected behavior. Code validation ***. Use unit tests covering boundary conditions like single-node graphs or fully connected networks. Conclusion: graph algorithms remain indispensable tools for solving complex interconnectivity problems. From fundamental traversal methods to sophisticated pathfinding techniques, mastering these algorithms unlocks powerful capabilities in software development. To deepen proficiency, engage actively with coding platforms offering graph-related challenges. Experiment with variations of classic algorithms to grasp nuances in application contexts. Consistent practice transforms theoretical knowledge into practical expertise.